doing today? Thanks for stopping in. Now that we finish up curve sketching, our next goal is to just finish up some of the calculus concepts from this course that I really think are going to help you out for next year. So we've looked at the power rule, product rule, the quotient rule. We still have not done the chain rule, so that's what we're going to move on to next. As it turns out, the chain rule's been hiding in plain sight all along. All right, let's get to it.
So let's start by looking at an example that we are already familiar with. We can take the derivative of this function, and I introduced the derivative by calling a rule the power of a function rule. And the idea being that, look, we knew that if we took the derivative of x to the power of n, that's n times x to the power of n minus 1. And I told you, well, if the base of the power was some other function, then what you could do is you could apply the power rule and then multiply that by the derivative of the base, in this case x squared minus 2x, which gives you 2x take away 2. Of course, you could simplify that or do whatever else you wanted. Now, most people don't really refer to something as the power of a function rule. Yes, it's true. You know, I didn't teach you something that wasn't true, but we tend to call it the chain rule. The chain rule being a more powerful rule for differentiation that basically says, look, anytime you have a rule for taking the derivative, if the rule will also apply to a composite function. So in a way, this is a function within a function. We have a power, but the base of the power is some other function, in which case we multiply its derivative as well. And that actually applies to any rule for differentiation, not just power rules. So let me give you a few examples. I'll introduce the chain rule, and then we'll see what I mean here. Okay, here is the chain rule. Notice we're starting in Leibniz notation. It's much simpler in Leibniz notation. If y is a function of u, so think about y taking u as input. And u is a function of x, so think about u as taking x as input. Then dy by dx equals dy by du times du by dx. That's what the chain rule is. So you can kind of imagine you start with input x, you put that into a function u, and then you put that into a function y. That makes y what's called a composite function, a function within a function. And that's exactly what we did up here. In this case, our u value, was x squared minus 2x. And if we treat u as x squared minus 2x, then our function was really y equals u to the power of 4. And we took dy by du and multiplied it by du by dx to find the derivative. Here our dy by du is 4u cubed. Well, u, though, is actually x squared minus 2x. That's why you see x squared minus 2x here. But you could think of this as 4u cubed times du by dx, which would be 2x take away 2. So let's actually do that. I went through it. I walked you through it in words, but we can say that in our above example, y equals x squared take away 2x to the power of 4. We can say let u equal x squared minus 2x. And so y equals u to the power of 4. Okay. And we can now say dy by dx equals dy by du times du by dx. Okay, dy by du is 4u cubed, and du by dx is taking the derivative of this right here, which would be 2x take away 2. And there's our derivative, dy by dx. Of course, we're going to probably replace u with 2x minus 2. Sorry, not 2x minus 2. That's the derivative. It was x squared minus 2x times 2x minus 2. Now that, of course, when we want to take the example, you wouldn't do it this way. I'm just showing you how it's the chain rule. How you're actually, when you take the derivative of this function here, you're actually using the chain rule. You don't need to introduce u to do that. You don't need to write all this stuff down. You can just do it the way you did it up here. So in a way, I haven't taught you how to do anything new. I'm just teaching you a new concept, this idea of the chain rule. Now, we could combine the power rule with the chain rule, and we could say something like the following. If y equals u to the power of n, then dy by dx is n minus 1 times du by dx. And that's actually an appropriate way to rewrite the power rule and say this is how the power rule works. If you have u to the power of n, the derivative is n times u to the power of n minus 1 times the derivative of u with respect to x. So basically taking this, taking the base and multiplying it by the base's derivative. You also see something like this. You'll see du, like this. Notation is common too. That is equal to n un minus 1 times du by dx. I'd like to point out that we can use the chain rule multiple times with any variable names that we like. We might have more than 3 variables, y, u, and x. We might name the variable something else. So the chain rule, take a look at these expressions I have here. Let's start with the first one. dA by dt equals dA by dr times dr by dt. That's true. That works. Notice I'm looking for the derivative dA by dt, and sure enough, it ends with dA by dt. See the chain here? dA by dr times dr by dt. Notice the variables all match up. Okay, if we imagine dy by dx equals dy by du times du by dx. Okay, see that chain, how it follows like that? So this one works. This basically says, oh, look, you take t as input to r, and you take r as input to a. So a is a composite function made up of with these two variables. This could be an example where you're looking at the rate of change in the area of something compared to time. So dA by dt might be the instantaneous rate of change of something with respect to time. Well, that would be dA by dr. Maybe r is the radius of a circle. So this could be, how does an area of a circle change with time? Well, the time changes the radius, and the radius changes the area. So imagine a radius of a circle that's growing over time, and you want to know the rate of change of its area. Then this might be a place that you would use that. Okay, let's look at this next one. Seems super complicated, but let's see if it works. dz by dx. So we start with z and we end with x, so that's good. And sure enough, there's that chain. dz by dy times dy by du times du by dx. This kind of implies we have a chain of functions x to u to y to z. So there we go. And this will always be true. No matter what the context is, even if we don't really think of these variables as y and u existing, I know just by looking at this expression that it's true because it follows the chain rule. Okay, let's look at some that don't. So these next two don't work. dy by dx equals dy by dr times du by, oops, do you see the issue we have with the dr and the du? Those need to be the same in order for it to work. So we could make this correct if we rewrote this as, say, dr. Okay, now it works. And let's look at the next one. dx by ds by dt times dt by dx. So the chain works here, but it doesn't produce dx by ds. It actually produces ds by dx. I know you might be a little bit confused right now, but I'm just trying to show you how you have these chains of functions. Like if I rewrite this as ds by dx, this kind of means I've got x as an input to t and t as an input to s. So s is a function with respect to t, and then t is a function with respect to x, in which case ds by dx would have to be ds by dt times dt by dx. You can do the chain rule in prime notation. It's just a lot more difficult to understand. If h of x is f of g of x, so think of a function inside a function, then h prime of x is f prime of g of x times g prime of x. So this idea of multiplying by the derivative of g of x probably makes sense, but this notation here can sometimes confuse students. We're basically saying it's f prime, not of x, but of g of x. So taking the derivative with respect to whatever g of x is. By the way, f of g of x could also be written, remember that notation right there? with that's supposed to be a dot there, not the word fog. So the composite function f of g of x. Now, one thing that might be a little confusing is that the chain rule is not immediately giving us any new functions we can take the derivative of. We've already been using the chain rule without knowing it. So, we do a question like this. We can take the derivative the exact same way you normally would. Just understand now that you're using the chain rule. So here f prime of x is 1/2 3x squared minus x. So that's the first part of the chain rule. That's this right here, this first underlined part. F prime, where g of x is the inside function. So then we multiply by g prime of x, the inside function, 6x minus 1. Oh, sorry, that's to the power of -1/2. Okay, the power rule. And then, of course, we simplify that. We get 6x minus 1 all over 2 times the square root of 3x squared minus x. We could use the chain rule to sort of simplify this problem. Look at this equation. It is an ugly, ugly mess. But if we wanted to, we could do the following. We could let v equal 3 take away x squared. Since 3 take away x squared, I see it in a few different areas here. And then I could take u, and I could say u is now equal to 4v plus 3v to the power of -1. And I did that because I noticed, hey, look, this is 4v plus 3v to the power of -1, and so is this, 4v plus 3v to the power of -1. So I see that the u now is like all this and all this. And then finally, I could say, now y is now equal to u to the power of 5 plus u cubed. Now, there are other ways you could write this out. This one just works nicely. It has some patterns in it. It has this, the square brackets are the same. So I've said the square brackets are kind of our u stuff. Okay, and then I've got 3x minus squared. I've called that v. Now, I've now created the following. X is input to v. V is input to u. And u is input to y. So I just turned this into a composite function. And I know that dy by dx is equal to dy by du times du by dv times dv by dx. And it makes it a little bit simpler to find the derivative now. So let's do that. So dy by du, I'm just taking the derivative of this right here. Okay, that will be 5u to the power of 4 plus 3u squared. Okay, next one, du by dv. I'm taking the derivative of this right here. So du by dv would be equal to 4. Okay, take away 3v to the -2. And then finally, after that, I'm taking the last derivative. dv by dx is just going to be -2x. Okay, now we are looking for the slope of the graph, or sorry, slope of the tangent to the graph at x equals 2. Well, when x equals 2, we should notice that means that v is going to be equal to 3 times 2 squared, which is -1. And u will be equal to, you'll get -7 if you look at that. Okay, if you take 4 times -1 and add 3 times -1, you get -7. So we can actually fill those values in down here. So u equals -1, so we get, sorry, u equals -7, so we get 5 times -7 to the power of 4 plus 3 times, just make sure I'm doing that right, yep, 3 times -7 squared, all of that times 4 subtract 3 times -1 to the power of -2 times -2 times 2. So there we go. Just a matter of figuring that out. And you actually get -48,608. Not that it really matters. We don't really, doesn't really matter. That part doesn't really matter. It's a big number there. Now, part of the thing that's frustrating maybe with the chain rule, like I said earlier, is it doesn't teach you how to do anything different. So let's introduce a new derivative rule. We haven't talked about trigonometry this year, and I don't know that we'll get to much of it, but if you were to find the derivative of sine, you'd actually find the derivative of sine is cosine, which may not be too surprising. Sine is a periodic function, so it's not a shock that its derivative is also going to have to be a periodic function, in this case cosine. Well, now that we know the derivative of sine is equal to cosine, that means we can actually calculate the derivative of all sorts of trigonometric functions. For example, this one right here, dy by dx. Notice there's a function inside the sine function. So its derivative, the derivative of the sine function is cosine. Multiply that by the derivative of what is on the inside function, which in this case is 6x minus 4. So the derivative of this trig function will be 6x take away 4 times the cosine of 3x squared minus 4x. We usually write that first factor out front. How about f of x equals 10 times the sine of root x? Well, f prime of x is, okay, so we just keep the constant out front using the constant rule. The derivative of sine is cosine, so the derivative of the sine of the square root of x is the cosine of the square root of x times the derivative of the square root of x. Now remember, the square root of x is the same as x to the power of a half, so its derivative ends up being 1/2 x to the power of negative a half. Simplify that a little bit to 10 times a half is 5. Cosine root x, and then we would have a power of negative a half, gives us this right here. Okay. Can we prove the chain rule? Well, sort of. Here's my proof. Let y be a function of u and u be a function of x. That makes y a composite function. X is input to u and u is input to y. Okay, we want to find dy by dx. A simple way of talking about the derivative, especially when you're dealing in Leibniz notation, is to talk about the limit as delta x approaches 0 of delta y divided by delta x. So that's from the slope formula, change in y over change in x, but the instantaneous rate of change is the limit as our delta x approaches 0. Let's take that and let's multiply it by something. In this case, delta u divided by delta u. We can then rearrange that so it looks more like the chain rule. In fact, we'll then write the limit in two different spots. Like that. Now, one thing we can look at is since u is a function of x and y is a function of u, it would make sense to say that as the change in x gets closer to 0, the change in u should also get closer to 0 as well. Since u is a function of x, as you bring the rate of change, the change in x closer and closer to 0, then the rate of change of u is also going to start to approach 0 as well, which means that we can replace delta x with delta u. And what do we have here? Well, now we have the limit as delta u. I made a mistake there. Sorry about that. I'm just going to fix this as opposed to re-recording it all, if you don't mind. This should be delta u approaches 0, and I'm going to leave that as delta x approaches 0. And sure enough, what do I have now? Now I have dy by du. And here I have du by dx, which is exactly what I wanted to show. That dy by dx is dy by du times du by dx. Now that's not a complete proof. The problem is with this line right here. The real proof is longer and quite tedious. The problem with this proof is it assumes that as delta x approaches 0, delta u approaches 0, it assumes that delta x doesn't equal 0. Or delta u doesn't equal 0. And that's a problem. That's not a fair assumption. That actually can happen, in which case this proof is no longer valid. Yeah, so our assumption there that's incorrect is that we assumed that as delta x approaches 0, that delta u would not equal 0. And it actually can happen. So the real proof's quite a bit longer. It's just an outline kind of to help you kind of understand why this works. So I've got some questions that I've assigned, some basic ones on the chain rule, and then some questions taking some simple trigonometric derivatives. Maybe I'll do one more example with you of a derivative that uses the idea that, look, if y equals sine x, then y prime, or dy by dx, equals cos x. What if you had a function like y equals the sine squared of 3x minus 1? How would you find that derivative? Well, the first thing to realize is, what does this squared mean? It means you really have the sine of 3x minus 1 all squared. And so we need to use the chain rule actually quite a few times here. Dy by dx will equal 2 times the sine of 3x minus 1 to the power of 1 times the derivative of the inside stuff. Well, the inside stuff's derivative is the cosine of 3x minus 1 times the derivative of 3x minus 1, which is 3. And we get 6 times the sine of 3x minus 1 times the cos of 3x minus 1. So there's another trigonometry one to help you out. Do your best you can with some of those questions. It might be a little challenging. And I'll see you soon.